So for our second session, we're devoting it to science. The adulteration of honey is a very complex, sophisticated, and intentional process. And in order to detect it, we need to make use of the best scientific technology available in order to identify whether this liquid gold is authentic or not. And to help us to understand this, we're going to be chatting to two scientists. First of all, we're chatting to Shannon Riva from FACTS, and she's going to be talking to us about how we can go about identifying and testing particular aspects of honey to understand whether or not it is an authentic product. And then secondly, we're going to be chatting to Dr. Grant Hall. He's part of a very key research group at Pretoria University that are looking at honey, doing a large number of surveys to determine whether or not honey in South Africa is adulterated. So sit back for a really good dose of science.
Good day, my name is Shannon Riva and I work for FACTS in Stellenbosch, and today I'm going to be speaking about honey authenticity testing. Before I get into the presentation, I thought it's important to speak about what is meant by fraud. Food fraud is the deliberate and intentional adulteration or misrepresentation of food for economic gain. Food fraud is a major issue worldwide. Interestingly, honey is the third most faked food in the world, behind milk and olive oil. So let's say you have a sample of honey that you'd like to test, but after a quick internet search, you're bombarded by the amount of test options that are out there. Let's say you decide to go with a sugar analysis, and again, there are so many different methods that can be used to determine the sugar profile of a honey sample. So how do you know which one is the right one to pick? Unfortunately, there isn't a test that does it all. So you need to ask yourself, what information do I need to know about this sample? Honey authenticity is determined by various factors, namely honey production, which is broken up into the processing side of things, as well as the potential adulteration, and then also the honey origin side of things, which refers to the geographical origin as well as the botanical origin. So how do we go about testing honey authenticity? There are various different approaches, with the traditional approach being sensory analysis, pollen analysis, or physicochemical analysis, or a combination of these techniques. These techniques often require experienced personnel and have a low sample throughput. So modern approaches make use of chromatographic methods, spectroscopic methods, stable isotope methods, and electrochemical methods. From the time honey is removed from the hive, every processing step has an impact on its quality. A loss of quality is often inevitable, but it's important that honey is never heated or processed to such an extent that its essential composition is changed. Various quality parameters are regulated to protect both the consumer and the market. Physicochemical methods remain the go-to for testing honey quality. The tests represented on the screen are the most common, and each of them tell us something different about a honey sample. So for example, HMF content and diastase are indicators of overheating or prolonged storage. Proline and moisture content indicates honey ripeness, and moisture content specifically is important for shelf life, as a high moisture content may cause the honey to ferment, spoil, and/or lose flavor. Water-insoluble solids content is an indicator of impurities, and this is dependent on the method of extraction of the honey. And pesticide residue analysis and microbial analysis are indicators of handling, which are very important aspects for food safety. Now that we've spoken about the quality side of things, what about honey adulteration? Honey is an easy target for adulteration. And what makes it even more difficult is that most adulterated honey will often test as compliant to quality criteria set out by local and international standards. Therefore, specific tests need to be conducted to determine adulteration. Stable isotope analysis, density, and sugar profiling, looking specifically at the sucrose content, are the most common tests out there to look at the adulteration of a sample. Stable carbon isotope ratio analysis is widely implemented throughout industry and reported throughout literature. This method is based on the principle that honey is made from the nectar of C3 plants, whereas sugar syrups that are commonly used to adulterate honey are made from C4 plants like corn and cane. However, fraudsters have found a way around this test. Rice and beetroot are C3 plants, so rice syrup and beet syrup are honey adulterants that would go undetected by the stable carbon isotope ratio analysis. This highlights the urgent need for scientists to stay on top of food fraud trends and constantly look for solutions to detect food fraud. So what can be done instead of the stable isotope analysis? Well, sugar syrups, whether they're of C3 or C4 origin, contain detectable levels of oligosaccharides with a high degree of polymerization, whereas recent studies have shown authentic honey to contain an absence of oligosaccharides with a higher degree of polymerization. Therefore, a more suitable approach to honey testing may be to look for the presence of oligosaccharides rather than to do the stable isotope test. Moving on to looking at honey origin, the traditional approach to testing honey origin has been through pollen analysis. Although this technique has several advantages, specifically looking at the pollen that is present, but also the pollen that's absent from a honey sample, there are various drawbacks to this method. This is that there's a low sample throughput, the fact of seasonal variation, experienced personnel are required, as well as a comprehensive collection of pollen, and also that some pollen may be underrepresented in certain flora due to just natural low pollen counts. So several modern techniques have been explored for determining honey origin. These include the methods listed on screen. Pretty much all of these methods have shown to be successful in determining both honey origin from a botanical perspective and a geographical perspective, but some are by nature better for distinguishing one or the other. So for example, NMR has been widely reported for distinguishing honeys of different botanical origin, whereas ICP-MS, for example, is better for distinguishing honeys of different geographical origin. These techniques are largely based on the use of discrimination markers to distinguish honey origin, such as phenolic compounds, volatile organic compounds, minerals and trace elements, and then amino acids, proteins, and carbohydrates. Discriminative markers may be used quantitatively, so to tell us how much of a particular honey is in a sample, or qualitatively, where you can screen an unknown sample and basically know what kind of honey it is or what floral source it came from. The markers may also be more prominent in monofloral honeys compared to multifloral honeys, and they're also influenced by climate conditions and soil characteristics. The use of chemometrics has been shown to be a valuable tool in extracting information pertaining to honey origin. So why is testing for honey origin so important? Well, the blending of honeys is a major issue in South Africa. Currently, South Africa can only produce 50% of the market demand for honey. So honey has to be imported from countries like China, Romania, and Argentina. Although it would be preferable to have a once-off commercial test where we can screen a sample and know exactly what it is and where it came from, implementing tests for origin are specifically challenging because they require a combination of modern techniques, a very large sample set to capture all the different types of honey that could possibly be in South Africa, as well as the use of chemometrics. All right, now we've spoken about the testing, let's go on to talk about what are the testing requirements as per South Africa's honey regulation. In our country, we have a regulation R835, which was published over 20 years ago. Yanush will be speaking about this in more detail later, but I'll be focusing on the different testing aspects of the regulation. R835 identifies various tests for determining the composition, ripeness, and quality of honey. These tests are listed on screen. The regulation states that any of these tests may be selected, and if the honey does not comply with any one of the selected tests, then it shall be deemed as not complying to the standards for the grades of honey. As you can see, many of the tests on screen we've already discussed throughout this presentation, namely HMF, density, the sugar profile, diastase activity, proline content, moisture content, and water-insoluble solids content. But where are the tests for the oligosaccharides or the pesticides, the microbial quality, or the tests for origin? This highlights the potential need to review the regulations and include these tests to keep up with scientific advancements and make sure that we're doing our best to check that honey out there is authentic. So how does RA35 compare to Codex? The parameters listed on screen are all the ones listed in our regulation with the different specifications. If we put them side by side from Codex, we can clearly see that there are some differences. Interestingly, Codex makes provision for the essential quality factors as well as the additional factors that can be tested. So the factors in green, your honey has to comply to them, whereas the factors in blue, it's kind of optional. So it's more looking if you're interested in the quality of your honey. If we look at the two regulations side by side, there are very noticeable differences, namely the HMF content, where Codex provides a higher limit for tropical regions, sucrose, where Codex provides provision for different honey types, diastase activity, where there's provision for honey with a low natural enzyme content, and water-insoluble solids, where there's provision for different extraction methods of honey, to name a few. Another question to ask is if the current regulations are appropriate to modern South African honeys. There is a major apparent knowledge gap pertaining to the composition of new honey types in South Africa, namely macadamia honey or buchu honey, for example. RA35 has not been updated since 2000, so some of these new honeys are not captured in RA35. It's important also to note that there is a lack of information pertaining to these new honey types, and so it's difficult to update the regulations to capture them if there isn't this knowledge available. The last important question to ask is, do the current regulations allow for fraud? Although this question is definitely up for debate, in my personal opinion, no, they don't allow for fraud. However, they may not also capture the new honey types in the specifications. So for example, a new honey type may have a naturally higher sucrose content than 5%, and if you apply the current regulations to it, it would look like that honey is potentially adulterated. However, it could just be natural variation. So we need to further scientific studies in order to update these regulations and make it a fair playing field. A few important points to take away from today's presentation is that firstly, there are numerous approaches to testing honey authenticity. No single test does it all, so you need to know exactly what you want to test. There are major apparent knowledge gaps pertaining to the composition of new South African honeys. There is a need for the development of a test method or model that is specific to South African honey origin. And once this information has been collected, current regulations may need to be reviewed to reflect this data.